Welcome to your weekly installment of YouTube videos. Hopefully you've gotten to knock out your quiz for the week and you're getting to some of these slides. We'll finish off thunderstorms and tornadoes as we move into Monday and Wednesday of next week, and that'll effectively wrap up what we have for the upcoming midterm, which is a week from Monday. We'll talk more about that in class as well. So this video here is going to be on the shorter end, and we're only going to have one, as is the case when we move with our quizzes. So a little bonus when you have to take the quiz to maybe have a little less to deal with in terms of lecture. So in both lectures we ended off with this slide talking again about what's really going on in the development of a cumulus cloud. The idea that you may have a parcel near the surface that's warm and moist but not saturated. As it rises up in the atmosphere, it's going to cool at that dry adiabatic lapse rate until we hit the point of saturation, which is when relative humidity is 100%. And that may be shown with these lapse rates that are relatively steep. And once we get saturated, we start to form our cloud. But again, we're looking at our parcel of rising air, and eventually it becomes to where there's a point, maybe low in the atmosphere, maybe high in the atmosphere, where the parcel is no longer going to be warmer and therefore buoyant in the environment, and therefore it'll stop rising. And so here in this example, there's a strong inversion, and that would effectively stymie the development of these clouds. Again, the depth of your cloud is going to really be predicated on the depth of your conditionally unstable layer. How far up in the atmosphere can our parcel remain warmer than the environment? That's the whole premise here behind stability. Is our parcel warmer or cooler than the environment? And so in an atmosphere here to the left, you have a pretty minimal lapse rate of the environment, and so as our parcel rises and cools, it quickly becomes cooler than the environment. We end up with a really shallow cloud. We got some fancy terms here, some cumulus humulus and some cumulus congestus, and then our taller cumulonimbus when we have a deeper conditionally unstable layer. And again, how do we form these clouds? Orography can play one of those roles. We saw this in our lab this week, and so we're going to spend a quick moment looking over the canonical mountain problem, which is admittedly a little different in the book. We actually simplified in lecture relative to what's in the book. And so I talked about this idea especially of being on the windward side or the leeward side of a mountain, and how we oftentimes find a rain shadow on the leeward side. Basically the moisture gets wrung out as it goes up the mountain, and it's a drier parcel as we descend. And then sometimes we get some really pretty lenticular clouds. We kind of gloss over that for now. And so here's the mountain problem in your book. The idea again that you're cooling as you go up the mountain. You hit a point where the temperature and the dew point are the same. Continue to rise in the atmosphere again. Be a little cautious getting too worked up about the numbers that are here in the book. Keep the 10 degrees Celsius per kilometer dry rate and the 5 degrees Celsius moist rate. Understand that the moist rate can be variable, but other than that, you're good to go. And so here again, as we descend the mountain, our parcel is always going to warm. We're going to warm at that dry adiabatic lapse rate as you descend through the atmosphere. Here in the book, they add a little bit of moisture back into the parcel, but again, keep it simple. The fact that we've wrung out that moisture, made the clouds on the windward side, means that we're going to descend and we're going to dry out as we come down the mountain. And so you often, again, will find some of these rain shadows which can produce some of the world's deserts. And so that's all that we have in terms of stability. I'm going to see if I can tab properly over and start a little bit here in the same video about thunderstorms and tornadoes. We're just going to give the real cursory beginning and get into the meat of this starting on Monday. As always, a little bit of motivation to get you going on this Friday, or maybe Saturday, or maybe Sunday, or maybe another day of the week morning. One of the big things is, what do we need to get thunderstorms? The ingredients. Like many other things in meteorology, we look for a recipe. Sometimes the ingredients come together to form thunderstorms, and once in a while we're able to add a little bit more to the recipe and create some severe thunderstorms. And so we'll talk about just general thunderstorms and then what else is needed when the storms are expected to become severe. Different types of thunderstorms, anything from the single cell to the multi-cell to the supercell. Hint, they're not all equal in terms of strength and severity, and we'll break that down over the next few classes. And let's be honest, chances are good if you're taking this class, whether it's as a major or whether you're taking it to fulfill your gen ed requirement, thunderstorms and tornadoes are kind of one of the more interesting things to study in this class. So hopefully you're able to take a little bit of enjoyment and a little bit of good learning out of this section that we're going to move through. And so one of the units to declare the frequency of thunderstorms in any given area is the concept of a thunderstorm day. Thunderstorm day is simply a day that experiences a thunderstorm. So if you have one of these days where you wake up and there's a little lightning and thunder at 7 in the morning and then it's a beautiful day, that's a thunderstorm day. If you wake up and it hails and has 29 tornadoes, hint, that doesn't happen. Either way, if it were to storm all day, that counts as a thunderstorm day. It's simply a day in which one exists. And so we can see here some interesting features. Again, the couple things that should stick out are the high numbers across the southeast and our circled area there over Florida, a general high number east of the Rockies, and then significant drop off if you get out to the western United States. Again, our main source of moist air is going to be the Gulf of Mexico, and the Rockies do a really good job of blocking that from making to the west coast. So if you're sitting here thinking thunderstorms are interesting, but I really don't like them, Central and Southern California could be a decent place to aspire to move down the road. You can notice a couple other interesting features, again, across Florida, the circle and Y. So hopefully you're thinking about that. The general reason for that is going to be what we discussed a couple weeks ago, the land sea breezes, helping to formulate thunderstorms. There are about 1 out of every 4 days over the course of a year, especially as you get down to southern Florida and the Everglades. Good lifting mechanism, good regular sources of moisture and warmth year-round. You can also see a somewhat interesting little feature here in the lee of the Rocky Mountains. Again, some of the flow that can come off the Gulf ends up resulting in that upslope, that orographic lifting. And so we actually see areas out here in eastern Colorado that are primed for thunderstorms a lot in the summer, and you can get some pretty significant hail events, especially with some of the colder air aloft that occurs in this portion of the country. Around Valpo, yep, right around 40 days a year we might expect in terms of thunderstorms. So what are the general ingredients necessary for, as we phrase here, a convective thunderstorm, one that's forming due to general lift in the atmosphere? A convective storm is one that simply has thunder and lightning. That's how we're going to define our thunderstorms. We're looking for a scenario in which we have warm, moist air rising upward in what's known as a conditionally unstable atmosphere. Remember, with our instability, when we're talking about conditional instability, we're saying, hey, is there something, whether it's daytime heating or orography or a front that's able to push our parcel up to a certain level upon which that it can continue to rise freely in the atmosphere. And that's the general premise in a conditionally unstable environment. So what do we need? We need 3 things. We need moisture, instability, and lift. Moisture, instability, and lift. And so where do we find our moisture or humidity? Typically from a maritime tropical air mass. Again, reasoning why we see these quite commonly in the southeastern United States. We need some form of instability, this energy in the atmosphere. And also we need a source of lift, something that is going to provide an initial force upward to get our thunderstorms to develop. And so I'm not sure why that was up there with a weird little bullet, so let's put everything up there right now for you. The first type of thunderstorm, and the one we're going to discuss in this video, is the single cell thunderstorm. It is the simplest form of a thunderstorm, existing with only an updraft, downdraft pair, a single one. They're not going to be long-lived storms. They're going to typically last for 15, 30, maybe 45 minutes before they dissipate and are no longer an issue. 3 stages, which we'll talk about in the subsequent slides. And these are going to be found in an environment that does not have a high amount of instability, and this other term here, shear. We'll talk more and more about shear as we get into the multi-cell and supercell, and especially as we start to talk about storm severity. Your book will refer to these as ordinary cells. If you've ever heard the term air mass thunderstorms, again, the idea that you have a warm, moist air mass, and we kind of saw this back when we were discussing clouds in the stability section. You get these little pop-up cells here and there that may seem to have no rhyme or reason, and these are going to be the ones that you get a storm here in Valpo and your friend 10 miles away, it's just simply a sunny day. And so that's often what we find with single cell thunderstorms. And so here's the overall schematic that will break down into 3 sections. You have your cumulus stage on the left, or the first stage, followed by the mature stage, and our poor little house there with a single tree in the middle of nowhere just escaped that nasty lightning bolt, followed by the dissipating stage. And again, this is going to be something that occurs over a relatively short time window, maybe 15, 30, 45 minutes. And so starting off in the cumulus stage. Cumulus stage, we have some type of convection occurring at the low levels. This could be because we do have lifting due to terrain, some type of a front, or it could be simply that it's getting warm in the afternoon and our parcels are able to rise to the point of reaching saturation and forming a cloud. The updraft, rising motion in the cloud, upward, draft that's moving upwards. This is going to be the stage of a single cell thunderstorm in which there's only rising air. So you may have noted on the last slide briefly that there was precipitation in the other 2 stages. Here we simply are forming our cloud, but it has not yet gotten to the point where we are expecting some type of precipitation. This may be a scenario in which if the updraft stage is over your house, you again miss the thunderstorm, someone a little bit down the road gets wet when we reach the mature stage. The mature stage is simply defined as when precipitation starts to reach the ground. Again, here in this thunderstorm, we can see that we have rain, we have lightning, we have cold air interacting with that rising air within the thunderstorm. And so here we separate what's known as the downdraft from an updraft. Important to note, though, that in the mature stage, we have both the updraft and the downdraft, as opposed to the initial stage where we simply had an updraft, and then when we talk shortly about the dissipating stage where we have only a downdraft. The downdraft is going to be cool. This rain-cooled air is being enhanced by what's known as entrainment, dry air moving in from around the thunderstorm. And so this is why, if you maybe think back to sometimes when you've been affected by thunderstorms, it really cools off when you get this type of a setup. That cold air can be, or is more dense than the warm air, and that can kind of start to work its way outward as it hits the surface. Again, cold air sinks, and that cold air can spread laterally along the surface, and it's really showing in the schematic that it's kind of cutting off this warm air, this fuel for the thunderstorm. This updraft is needed to sustain a thunderstorm, and as this occurs, we start to lose our thunderstorm. You may see an anvil. We'll talk more and more about anvils as we move forward. Anvils of thunderstorms are going to suggest that you have a level in the atmosphere in which the parcels of air can no longer rise. You may hit an inversion or some other stable air, and it spreads out horizontally across the sky. Again, the idea of a gust front, we'll spend a little more time talking about gust fronts more here in the supercell stage, but here we're looking at the gust front working its way ahead of a storm. So if you've ever seen a feature like this, one of these very low, kind of menacing looking clouds, this is going to be the idea of a shelf cloud, or again, something related to that cold air, the precipitation driven air that's moving ahead of your thunderstorm. And so yeah, sometimes this comes in, it gets chilly even before it rains, it might get kind of breezy, and this is going to be that leading edge of the cool down draft air. In fairness, sometimes these are quite pretty. Again, that's a picture that I took quite a number of years ago from my backyard, and again, looking at some pretty neat features associated with these gust fronts in the sky. Again, they look pretty scary and they can produce some strong winds, and we'll talk more about that later on when we get into severe thunderstorms. And so let's wrap it up here with the dissipating stage. As I already brought up, this is when the updraft has been cut off by the sinking air and the precipitation cooled air. The rain is typically starting to lighten up a little bit because we are no longer fueling our storm. You can see in this image that we're kind of left with a lot less cloud. It may start to break up and look pretty ragged. We still may be left with one of these anvil features up at the top of the troposphere. And so in this example, we see some neat rays, some crepuscular rays coming down out of the cloud. And again, starting to erode, you can almost see in the middle of this that you wouldn't be getting much precipitation as this storm dissipates. What's happening? That cool outflow air and the precipitation simply cut off our inflow, and that's going to cause our storm to, again, live a very short amount of time, and this is going to be in the absence of that idea of shear. And so shear is going to become the interesting ingredient as we move forward in class on Monday and Wednesday to help us delineate between these single cell storms, which very rarely are going to result in any type of severe weather, to the multicells, which sometimes will, sometimes won't, to the supercells, which are the common producers of severe weather. All right, 15 minutes. That's what we got for Friday. Have a good one, and we'll see you on Monday.